Hey everybody, welcome back. So we've been talking about the evolution of stars, how they're born, how they age, how they die. Some will die in a supernova and push all this gas out into space that'll form the next generation of stars. Small stars like our sun will become a planetary nebula and it still puffs out those outer layers. So that again, that gas is going out into space. So when we're talking about the life cycle of stars then, what we need to understand is that it's all forming from this same gas, that the previous generation of stars leads to the next one. So what we're going to talk about today is that gas and dust that's in between the stars, that's going to lead to forming the next generation of stars. And we call that the interstellar medium, although that's too much to say, so I'll almost always call it the ISM. So let's get started. Okay, so as I said, we're going to be talking about the interstellar medium. That's just the space, the material, the medium is the material between stars. That's what interstellar means. So keeping up with this interstellar medium then not only is going to tell us about how new stars are born, but also when we start looking at galaxies, that's going to tell us a lot about what's going on, where star formation is taking place in these galaxies. So have your class notes out. Looks like this. Front and back of both pages, both sides as always. And pause the video until you've got that out. Okay, so this is looking towards the center of the galaxy. That picture that we showed last time is the center of the galaxy is right about here or so. But you see that it looks like there's missing stars here. It looks like, I've got this weird shaped cluster here. But in reality, the central bulge of the galaxy is pretty much a ball. It's pretty spherical. There's a big black dust cloud in between us and the center of the galaxy that we can't see through. So what I want you to start getting in your mind, and I'll reinforce this later, is that they're the same number of background stars like you see here everywhere that you look, pretty much. So when I have an area where it looks like there are fewer stars, that just means that I've got some sort of dust cloud in between and only the brightest stars are able to shine through. So these stars that you see right here are behind the dust cloud, but they're so bright we can actually see them through the dust cloud. But most stars are not going to be bright enough to penetrate through. So this interstellar medium then is all of the gas and dust that's in between stars. Some of it is spread out throughout the galaxy. A lot of it are in these large clouds like you see here, this area forming in here. It is mostly formed of hydrogen and helium. Don't be fooled. Remember, this is the stuff that's making up stars. 90% of everything in the universe is hydrogen and helium. So if you don't know the answer, that's your first guess. But in the case of these clouds, they are almost all hydrogen and helium. That is going to lead to form the next generation of stars, which are then also going to be made of mostly hydrogen and helium. But there is a little bit of other stuff, some other gases, and then some dust. Now this dust is really more like soot or fog. It's very, very tiny particles. It's not, dust grains like you might sweep up off your table or something like that. So there are two effects of the interstellar medium, the two effects of these dust clouds on starlight. It can cause extinction, which basically means it blocks the light. So looking here in the middle, you see that no light at all is coming through. So that's extinction. It can also cause reddening. And you can see that in that the stars on the edges, the ones that are just barely able to shine through the thinnest part of the cloud, notice that they all look redder. Even over here, this tells us that there's actually, the dust cloud actually extends this far over into this part because it's reddening all this. It's just a lot thinner than what we find here. Let's see why that's true. So then this is following along on your worksheet here. So down towards the middle of the page. So in general, not looking at the page, but in general, what color are the brightest stars in the galaxy? So I'm not just talking about here in this picture, I'm talking about everywhere. What color are the brightest stars in the galaxy? Pause the video, think about that, circle it on your sheet. Well, you guys know from OBAFGKM, the spectral classes, that the brightest stars in the galaxy, the most luminous stars in the galaxy, are always going to be blue. They're going to be those O-type stars, those really hot stars. Now, what are the color are the stars at the edge of the cloud here? Well, we've already talked about that, but pause the video, go ahead and circle that. So right here at the edge of the cloud. Well, you see that they're all red, and I know they're kind of orange, but remember, there's only two colors in astronomy, red and blue. So these stars are bright enough to shine through the cloud through, now admittedly, only through the thinnest part of the cloud because it's thinnest on the edge than it is in the center. But these stars must be crazy, crazy bright to be able to shine through that cloud. So they must be actually blue stars, but they look red. And so the cloud is what's making them look red. So let's see how that works. The reason they look red is the same reason why the sky is blue. So when the light comes from the sun, all the colors are here. The whole rainbow is shining down on you. However, the water molecules in our atmosphere, the water vapor in our atmosphere, scatters the blue light. So in the sky out here, all of the rest of the light just keeps on going. The red and the green and all that just keeps on going past. But the blue scatters and it's coming from all directions. Your eye is not smart enough to trace those paths of that blue light back to the sun where it came from. So from your eye's perspective, you've got a billion tiny little blue lights in the sky that's coming at you. And this is why the sky looks blue. So it has nothing to do with oceans. It has nothing to do with, reflections off the ocean or anything like that. It's because that water vapor in the air is scattering blue light. So the blue seems to come from all directions. The red, on the other hand, passes on through. Well, we see this when we're at sunsets and sometimes at sunrise too, but particularly here in Arizona, where you look out to the west and you see the sun is setting. And what's happening is over there, over the ocean or whatever, they've got blue skies because it's daylight for them. But only the red light is passing through that atmosphere because all the blue light's getting scattered away. And so all we see is the red. That is the same thing that's happening with the galaxy, well, with the nebula that we're seeing out here. So the thickest part, I've got extinction. The reddest, at the edges, at the thinnest part, is where I'm getting the reddening. And so if I were able to stand up here, so the star's looking this way and it's looking red. If I were to stand up here, they would look blue because the blue light would be scattered off to the side here. But since it's coming straight at me, the blue light's scattered away, and it's just like those sunsets. The blue light is scattered in all directions, so the only thing that's making it through to my eye is red. So even though these are blue stars, remember they do have some red in them. We talked about this before. So only the red light is making it through. So how do we detect interstellar medium? How do we detect the ISM? Well, it's not putting out really any light to speak of because it's not a star. But so one of the best ways that we can tell is by obscuration of starlight. So in other words, it blocks the stars. So here you see that we've got all these background stars. Remember, this whole picture should look like this. Instead, though, I've got this area that we've sketched out here where it's all dark. So that tells you that between us and the background stars, there is this black cloud that's blocking the light. And so that's the only way that I can tell that it's there, is because it's blocking the light from that. So here's another example. This is actually one nebula, but then it's got a dark cloud in front of it. So it's not actually three different nebulae. This is all part of the same complex. It's just that there's a dark cloud blocking the light in between us. So I want you to start thinking about space in 3D. Don't think about everything, just being plastered on the sky. Think about looking out and seeing things in 3D, and all of this will start to make more sense to you. Another way that we can detect it is with the absorption spectrum. Now, you guys know that all stars produce an absorption spectrum. This happens to be showing the hydrogen spectrum here. But when that starlight passes through the cloud, this cloud is cooler and lower density than the star, even the star's envelope. So it produces a second set of absorption lines, and that's these narrower lines that we see superimposed on top of the star. If it also passes through a second cloud, like we saw on some of the previous slides, then I'll get another layer of absorption lines put on the top of it. So just like when you were trying to classify the different elements by, okay, I think this line goes with this, and this line, that might be iron, and we pull those out, we look at the rest. We do the same thing here. We look at this spectrum and we say, okay, this line, and this line are from the star, so let's get rid of that. Now, we've got two different thicknesses here, so let's look at the thickest one, and now we can start classifying the different elements that are there. Get rid of those. Now we look at the thinnest one. Now we're looking at what's happening with the cloud in between. So we can see that these clouds exist by looking at the absorption lines that appear. If we get more lines than that star should have, because I can measure its temperature and all that, then that tells me that there must be a cloud in between us. Another way that we can detect clouds is they actually are emitting radio. We can detect these things in radio. And this is a hydrogen atom, so I've got a proton and an electron here. And this gets into quantum mechanics that we're not going to deal with, but those things are spinning. And they have lower energy if they're spinning with opposite poles. So they're spinning, one spinning clockwise from the top, one spinning counterclockwise from the top. So as long as they're here, it takes more energy to maintain that than it does here. Not a lot more, but a little bit more. So what we'll see is that this will flip naturally. Just like that electron wanted to drop down into the lower energy state, same thing is happening here. In hydrogen, it wants to flip so that it's in a lower energy state. And the difference in energy produces a light wave, a photon, that has a wavelength of 21 centimeters. That's in the radio band. So radio astronomers then can actually look at these clouds and they can see that radio emission that's coming from the hydrogen atoms here, from the 21 centimeter radiation from that. Additionally, molecules in the cloud also vibrate in different ways. They've got different states, and so they'll drop down to a lower energy state, and they'll also emit some radio. Now, don't get confused. These molecules make up a tiny, tiny fraction, like 0.00001 of this cloud. So really what they are tracer molecules. So this is an example of showing how we can see what's going on. So this is a nebula, this red nebula that you see here. There's some dust lanes, some dark clouds on top of it. This is a star-forming region. When I look at these molecules here, these molecules are all contained within the cloud, but in very small percentages. The cloud is made of hydrogen and helium, plus a little bit of extra stuff. And so there'll be carbon monoxide, ammonia, methyl alcohol. This is not the stuff that you drink. This is what we call wood alcohol from where I'm from. This is the stuff that's poison. If you get more than about 5 milliliters of it, you'll die. Anything less than that, you'll go blind. So never, ever, 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 ever drink homemade alcohol, because a lot of times it's got methyl alcohol in it as well, and it just doesn't take much to kill you or blind you. Ethyl alcohol, that's the good stuff. This is your pure grain alcohol. So, you know, Benjamin Franklin said that alcohol, he said beer, but alcohol is proof that God loves you and wants you to be happy. Well, it's actually out in space. It's written in the universe, man. Formaldehyde, that's actually what if you ever took a biology class in high school, that's what they used to preserve the specimens, that kind of stinky liquid that you would pull out before you dissect the pig or whatever it is you ended up dissecting. So all of these molecules then exist in the cloud, but again, in tiny, tiny amounts. The reason we care about these is that they emit radio. Those are those interstellar molecules, this is formaldehyde here, that emit radio light. So when I look at the radio, so these little curves here are showing the concentration of radio. This yellowish green one here is looking at formaldehyde. And you see that the greatest concentration is actually right here, which is in the darkest part of this cloud. You see how it's dark underneath? So this tells me that this is where the next star is going to be born. So we've already had a star be born here out of the cloud, and that's lighting this up. That's what's turning it from a dark cloud into a bright cloud. However, right here, it's still dark, but it's much more dense. And I can tell that because of the amount of formaldehyde that I've got there. Even though there's not much formaldehyde there, if there's a whole lot more hydrogen coming in, that's going to proportionately have more formaldehyde come in. And so that tells me that this is the next region that's going to start forming stars, even though I don't see anything here yet. So if I'm looking for protostars and things like that, that's going to be a place that I can find them. So there are 3 types of ISM, 3 types of nebulae. You need to know all 3. So one of the big things we need to know is what are the 2 effects on starlight: extinction and reddening. Then there are 3 types of nebulae. You need to be able to identify all 3. They're all clouds. They're all exactly made out of the same stuff. The only thing that's different is how they're being lit. So this is a dark nebula. So it's not lit from the inside or outside. It's very cold. And the only way we can see that is because it's blocking these background stars. So this is not an area of missing stars. That's a cloud that's floating between us and the background stars. An emission nebula is heated from the inside by these newborn stars. And we'll show you some close-up pictures of this. But this is a cloud that's a star-forming region. So some of these stars have just turned on. They're putting all this heat out into the rest of the cloud. The cloud is getting warm, and that's what's causing it to emit. A reflection nebula is caused by when I've got a nebula here. This is like the idea of reddening, and I've got some star behind it. The starlight that passes directly through is going to look red. The blue light gets scattered. But what if I'm standing up here? Now I'm actually seeing the blue light. And so that nebula is going to look blue to me because only the blue light is being reflected up to where I can actually see it. And that's what we see in this picture here. All right, so let's look at each of the three types. So remember, it is not missing stars. So this is a radio map. So I'm not sure which particular element this one's tracking, but like we saw with formaldehyde for that. And looking at the picture, you can't really tell where is the darkest part. This is certainly a bright star. It might be in front of us, or it might be passing through the cloud. We could tell if it were reddened or not. This is black and white picture, so we can't tell. But looking at the radio map, we see that the densest part of the cloud is right here. And then it gets less dense as we move up through this area here. So by looking at radio, we get a whole lot more information than when we get just from using the visible light. And that's why we need to use the entire electromagnetic spectrum to understand what's going on. All we get from stars is light. We've got to squeeze every piece of information out of that light that we can. Here's one of the more famous dark nebulas here. This is a bright nebula called the Flame Nebula. This is in the constellation Orion. This star right here is one of the stars in Orion's belt. So if we're looking at the three stars of the belt, it's this one over here down on the lower left. This is called the Horsehead Nebula, as you can probably tell, because it looks like a chess piece, like a horse. But this is a dark nebula superimposed on the bright nebula behind it. If we didn't have this bright nebula, you wouldn't actually be able to see this. It'd just be a dark spot in space. So a lot of the pretty pictures that you see are going to be made of these different types of nebula. And here we've actually got three types of nebula all in one picture. But looking at this right here, this is going to be a dark nebula. Okay, so now that nebula gas is very diffuse. That means it's not dense. So it's way spread out. If you were inside it, you'd never know you were inside the nebula. And if you've ever been in a dust storm here in Phoenix, for example, you can see for a little while, but you have to look through enough of that dust before finally it stops blocking your vision. It starts blocking your vision. You can't see any farther. Same thing is happening with these clouds. We're talking about one atom every, mile or so, every kilometer or so apart. So these things are not dense at all. But when we look through enough of them, because they are, oh my God, huge, now it's enough that it can actually block the light from that. So newborn stars inside that cloud then can heat it. So looking at your worksheet on the back, at your class notes, what type of spectrum then is produced by a hot diffuse gas? Pause the video, circle the answer on your sheet. Okay, so we've got a very, very diffuse gas being heated up by these newborn stars. That's going to produce an emission spectrum. So remember that emission spectrums are those individual colored lines on a black background. Well, those colored lines are like theater lights. They mix together. Hydrogen, for example, when all of those lines mix together, comes out kind of a pinkish purple. It's red, because we only have red and blue in astronomy. But you can actually get a wide variety of colors from an emission nebula, depending upon what elements are there. And remember, it's mostly hydrogen, so they're all going to be reddish. But there will be some other colors in there where there are concentrations of other atoms that are glowing, because a hot, diffuse gas, whatever that is going to glow. If that gas, for example, has lots of green in it, green lines, then the gas is going to glow green. If it's got, lots of orangey lines, then it's going to glow orange. Okay, so anytime you've got either red or multicolored gas, then you've got an emission nebula. This is the second type. And it's produced just because it's simply an emission spectrum. So everything that you learned in spectroscopy applies here. So it's red here. That tells you that this is mostly hydrogen. But when we zoom in on the area that you see right here, this is a Hubble Space Telescope picture of this very same area. Then you can see that there's actually a lot of different kinds of gases other than just hydrogen. And that's what's producing all these different colors that we see. So if it's red or it's multicolored, then it's probably an emission nebula. A reflection nebula we talked about is blue because of that scattered light. So if this is my dark cloud and the light is coming through, it's going to be reddened because the blue light is being scattered up. But what if we happen to be positioned on the top? So the light comes through here, gets scattered, and then comes up. Well, all we're going to see is the blue. So this then looks blue because it's being lit from behind. The cloud itself is not being heated up. So this is not an absorption spectrum. Don't think about that. That's not what's going on. It's actually scattering the light. It's the same kind of thing that's making the sky blue outside. From other locations, like say, if I were on this side of the cloud, then that light's going to come straight through and it's going to look like a dark nebula to me. So this kind of shows you what's going on. Here's you, here's what's going to be the reflection nebula. And they're giving you an example of an emission nebula where I've got a newborn star lighting this up. But let's say just take the light from that star. So that's all we're worried about right now. So the light from the star comes into the cloud. The stuff that passes straight through is going to be red, but the stuff that gets scattered is going to be blue. So if I'm sitting down here, I see a blue reflection nebula. If I'm sitting up here, all I see is a dark nebula with the starlight behind it being reddened. So remember, this cloud and this cloud, there's no physical difference between them. The only thing that makes them look different is how they're being lit up. All right, so the last thing we want to talk about then are giant molecular clouds. We talked about that this is how stars are formed. Well, this is a map of a giant molecular cloud. This is actually a radio map showing you, so this is not the color that you see. You can't actually see these with your naked eye. Remember, they're very, very, very big, they're very dark, and they're very cold. But this, even here in radio, you can see that this cloud is clumpy. And so if this cloud gets a kick, it's going to start to collapse, but it's going to collapse around these brightest points here because that's the most dense areas, and that's what's going to end up forming individual stars in this star cluster from that. Okay, so summary, let me bring all this up here. You need to know the effects of nebula on starlight, extinction and reddening. Understand when I get extinction, that's when it's nice and thick. Reddening is when only I'm at the edge and then the blue light's being scattered away. Three types of dark nebula, or three types of nebulae. A dark nebula is black. Emission is mostly red, but can be multicolored. Don't let this fool you. If it's multicolored, it must be an emission nebula, even if there might be a little bit of blue in there. If it's multicolored, it's an emission nebula. Reflection nebula are always going to be blue because we're seeing that dark nebula, the scattered light coming through. Anytime you're asked what the composition of a nebula is, you always say hydrogen and helium, because that's 99% of everything that's in there. Tiny bits of other gas and dust that will eventually conform planets and puppies and kitties and unicorns and all that sort of thing. All right, so that's it for ISM. So download the practice worksheet. Looks like this. Going to have you identify some different types of nebulae, upload that, and then, as always, these will be graded for accuracy. Here's our live help. Be sure and come get that help if you need it. One of the disadvantages to being in an online class, as I mentioned last time, is that you're not getting that group interaction that is so critical for learning the material. It's a lot harder to figure this out on your own. So get in study groups or just come get me, even if you just want to hang out and do your homework while I'm sitting there, even if you don't have any questions at all. I'm sitting online whether somebody's there or not. You may as well come and keep me company, right? Okay. So the key thing that I want you to keep in mind here is that all of these different types of nebulae are actually the same thing. They're all mostly hydrogen and helium with maybe just a little bit of gas and dust of other types thrown in there as tracers. But what the primary difference between all these is how they're lit. If there's no light at all, it's going to be a dark nebula. If it's lit from the inside so that it's heating the cloud, it's going to be an emission nebula. If it's being shown by light from the outside that's being reflected up, then that's going to be a reflection nebula. But all of these are really the same thing. Don't get confused with that. And the other key thing that I want you to keep in mind is that anytime we see one of these nebulae, either there's been a supernova that's gone off or a planetary nebula has puffed that outer layers out into space, eventually that's going to come back together and form the next generation of stars. A lot of the pretty pictures that you see in astronomy magazines or whatever, a lot of them are nebulas. And the reason for that is because these emission nebulae can produce all these beautiful different colors that mix together really well. But again, it's all the same thing, and this is what's going to be leading to star formation, and what we're going to be using when we talk about galaxies and we're tracking where does star formation happen in the galaxy. We're going to be looking for those nebula. So that's where we're going to stop. We'll see you guys next time.